We know the masses of the two bodies, 2 kilograms and 3 kilograms. We know that they pulled to the right by a force of 42 newtons. We know that there is friction, and we're given the coefficients of kinetic friction between the surface and each of the blocks. 0,1 for the 2 kilogram block and 0,15 for the 3 kilogram block. And we're asked to find the tension in the rope which joins the two blocks. Here's an overview of the strategy we've gone through. You should now pause the movie and complete this by actually putting numbers in and doing the calculations. And when you've done that, press play again on this movie. So right now you should pause the movie. So let's now work through the solution. First step, we need to find the friction force acting on each of these bodies. We substitute the relevant values into these equations. The coefficient of friction for the 2 kilogram object is 0,1, and the normal force is its mass, 2, multiplied by acceleration due to gravity, 9,8. The friction force acting on the 3 kilogram object is found by multiplying its coefficient of friction with its normal force. So its coefficient of friction was given in the question as 0,15. Its normal force is equal in magnitude but opposite in direction to its weight, which is 3, not 2. 3, because it's a 3 kilogram object, multiplied by acceleration due to gravity, 9,8. And so that gives us these answers. In both cases, friction is acting to the left because the system is moving to the right, and whenever an object moves, it experiences friction in the opposite direction to its motion. We choose the right direction to be positive. The net force acting on the system is the vector sum of all the forces acting. Vertically, we don't need to worry because anyway those forces are in equilibrium. So we only focus on the horizontal forces. So we take all the forces acting to the right and subtract away the forces to the left. But we don't need to include the tension force because the tension force to the right on the 2 kilogram is equal and opposite to the tension on the 3 kilogram. So those two forces cancel one another out. So they are actually within the system. They don't act from outside the system, and therefore they are not part of the net force acting on the system. And so we can just ignore them when we are calculating the net force acting on the system. So the net force acting on the system is equal to 42 newtons, which acts to the right, minus the 2 friction forces, which act to the left. So we just simply substitute those values for friction that we just calculated into this equation, and we find the net force acting on the system, and it is to the right. Now we need to find the acceleration of the system, which is equal to the net force acting on the system divided by the mass of the system. And that is the same then as the acceleration of either of the two bodies because the whole system accelerates together. So we know the net force acting on the system, we calculated it just now as 35,63. The mass of the whole system is 2 kilogram plus 3 kilogram, 5. And so the acceleration of the whole system is 7,13 meters per second squared. The net force acted to the right, and so the acceleration of the system is also to the right. So that's the acceleration of each of the blocks as well. So let's now focus on just the 2 kilogram block. We know that it's accelerating to the right, so there's a net force acting on it to the right. That net force can be found by the vector sum of the 2 horizontal forces acting on it. The tension to the right minus the friction to the left. We know the friction's value, so we can substitute that in. And that net force causes this 2 kilogram object to accelerate. And the relationship between the force and the acceleration is given by Newton's second law. F net is equal to ma. The mass of this is 2 kilograms, and we've calculated the acceleration of the 2 kilogram body. It's 7,13. We can rearrange this equation to make t the subject of the formula. T is equal to mass times acceleration plus friction. We substitute our values in, making sure that these all apply to the 2 kilogram body, not something else. And we solve and we find the answer, 16,21 newtons tension acting on the 2 kilogram body to the right. And that must be the same magnitude tension that acts on the 3 kilogram object, but just then to the left. So we can check if that is so by now isolating the 3 kilogram block. We know that the 3 kilogram block also accelerates to the right at 7,13 meters per second squared, but this is now under the influence of its net force, which is the vector sum of the forces acting on the 3 kilogram body. Again, we have the right direction as positive, so the net force acting on the 3 kilogram body is 42 newtons, which acts to the right, minus the 2 forces which act to the left. The tension, which is what we're trying to find out, and friction, which we've already calculated earlier. And that net force causes an acceleration, and the relationship is given by Newton's second law, F net is equal to ma. So we rearrange this to make tension the subject of the formula again, and we substitute values in, being careful to substitute values related to the 3 kilogram block, because that's what we're isolating and looking at now. So those are the values we should substitute. We do the calculation, we find the same answer again, 16,21 newtons, but it's now to the left. And that's simply because tension always acts towards the center, but the magnitude on either end is equal. So our final answer is that the tension in the rope is 16,21 newtons. And we don't really need to give a direction, because we know that that implies always that tension acts towards the center. So the direction of tension is always to the center of the rope.